Right. Good morning. Close that. Any questions or comments? Okay, I have one last piece of the picture, which is the most important thing in my opinion, which is also like connected to the research today. But I will try to just give insights of what is going on and why these things are so exciting for people. So I want to introduce so-called topological insulators, what they are and why they are like exciting. And I will do this over an example called Kane-Mele model. So this is exactly like Haldane model, but it is a little bit improved Haldane model. And if you remember, Haldane model is exactly like graphene, but a little bit improved graphene. Okay, let's first think about the broader picture. What we saw in this course was something like this, right? We have like 2D electron gas and strong B and low temperature. If you do these things, and then if you put your hands on a good transistor, like it's like these 2D semiconductors are actually transistors, and that's why the technology was so much delayed. What you're going to find is like this sigma xy is going to be just quantized, and there is like a wide range of delta B. This quantization is observed, and this quantization is observed 1 in 10 to the 10 or 1 in 10 to the 11 parts. So this is a gigantic quantization. And it is like so surprising that the first person who saw this, like Klitzing, he thought his voltmeter was, there was something wrong with his voltmeter. So this, how unexpected this phenomena is. And if you want, this is actually kind of like Isaac Newton noticing the gravity by the apple, or like, I don't know, maybe like the kind of like eureka moment, right? That happens once in a generation. And it was much more difficult because there were like material complexities, there was quantum mechanics, there's like microscopic observability, all these things. It was like a very fundamental but complicated problem. And how did we explain this? We explained this like there is like a wave function psi. This is like a quantum phenomena, and it has like a phase. Like there's like a phase degree of freedom, and there's like a gauge degree of freedom coupled to this phase. And all of these things gave us a structure which we called topology, right? And we defined something called Chern number of the band, and that was the big insights that we get from not only quantum Mole system, but also all kind of electrons in all kind of solids, which was like the band topology. And in Haldane model, we saw that it's actually not B, so B was not needed in Haldane model, but what was needed was time reversal symmetry breaking was needed. Right? If you break time reversal symmetry, Haldane showed that you still have this quantization, you still have this topology. Then the question is like, can we make this more generalized? Do we actually need time reversal symmetry breaking? One of the questions is, can we avoid TR breaking and still get this Chern number non-zero? Can we still have a topology in the presence of time reversal symmetry? And we said this Cn is element of integers. Are there other quantum numbers? And also, what about the dimensionality, right? So we were in 2D, and in the SSH case 1D. What about 3D? Can we have like three-dimensional quantum Hall effect? And lastly, like all of these things were defined for insulators, right, which had like a band gap. What about metals? If I don't have band gap, can I still define topology? Can I still define something protected? So all of these things are like related to research today, and there some of them are still like under research, but they all fall into the category of topological quantum matter. So typically we look at the matter and we just classify the phases of matter like liquid, gas, and so on, or like sometimes crystals, sometimes magnets, sometimes ferromagnets. But with the new ingredient of topology, we have a new way of looking at the matter, and that's what this whole research area is about. So today I want to give only one example. So I want to at least show you how we can avoid time reversal symmetry breaking, and I will show it through this so-called Kane-Mele model, and it's going to teach us a lot of things about what we already learned. So let me first start with graphene. And I want to add on graphene Haldane and so-called Semenov terms. So if you remember, okay, let's do that. So graphene has like two Dirac cons. One is at HK, one is at K, the other one is at K prime. And it was something like this: V sigma x px plus sigma y py. This is the usual graphene. And if you add this sublattice potential, you have like this Semenov mass. This is sigma z. And if you add also this next nearest neighbor hopping, like Haldane showed, you are going to have this M Haldane sigma z. But the difference for the other value is exactly like this, but first we have this minus, right? And K and K prime, they have exactly the same Semenov mass because sublattice symmetry is independent of, this is like about valley symmetry, but because this is about nearest neighbor hopping, Haldane mass changes sign. And what we said was like turn number of the K band is 1/2 sine, let me write it, Vx, Vy, and M. And so this one gave us something like 1/2 sine ms plus mh. I'm assuming both ms and mh to be positive, so this is that. And ck prime is 1/2 sine, again, Vx, Vy, M. And in that case, I have one minus here, another one here, so this is 1/2 sine M Haldane minus M Semenov. And because the total is ck plus ck prime, we have like a topological phase if M Haldane is bigger than M Semenov. Okay, that was the picture we obtained. Now I want to think about this result in terms of symmetries. Let's think about symmetries. First, what I can do is I can combine these two values by introducing a new Pauli matrix. So let's just copy this. And the new Pauli matrix I want to introduce is like will be shown with tau. So this is valley degree of freedom. if you are in K, this is going to be 1. If you are in K prime, it's going to be minus 1. It's exactly like a spin. There are like 2 degrees of freedom, but it is standing for something different. And because this one was plus for one value and minus for the other value, I am going to just put tau z here. And also I want to combine this ms and mz, so I can also put tau z here, because Semenov mass does not change from value to value, whereas Haldane mass is going to change sign. So what I'm going to do is I'm just going to combine these two and write it like that. Sigma z. Now there are basically two symmetries. One is parity. You may have figured that in condensed matter, when we say like chiral symmetry, parity symmetry, or like time reversal, we are meaning like a specific kind of operation, and you should always be skeptical about that operation, like because this, for example, what we call chiral symmetry is different in particle physics. So parity here is meant to be exchange of A and B sublattices. Okay, that's the meaning of parity. There are other parities that can be defined, but in this context, that's what it is. And if you exchange two sublattices, what happens is like sigma z. I think this one is. Oh yes. Okay, let me just try to. So this is sigma is sublattice, and tau is valley or Dirac cone valley. So this is k. This is about kk prime. Sigma is about AB sublattice. This is A or B. And if I exchange A and B sublattices, what I need to have is like this sigma z, which is standing for A and B. It's going to go to minus sigma z. So that means A and B interchange. So this means K and K prime interchange. And if you do this interchange, you need to pick up a minus sign because of this. And also I want to define time reversal. So to think about time reversal, I want to think about this Brillouin zone. It's like this, right? I mean, there are different ways to draw it, but that's how I draw a while ago. So this is K and K prime. And under time reversal, if you remember, P goes to minus P. I need to invert P. So what I need to do is I need to take this. And if you invert this, this is going to go to K prime. This is going to go K. Because I'm just flipping the sign of momentum. That means sigma z is going to go to sigma z. Okay, it's a little bit. So under A and B. So A and B degree of freedom doesn't know about time reversal. Whereas tau z, this is the flipping, is going to go to minus tau z under K and K prime interchange. So this is coming from change in momentum sign. Okay, now we can think about two things. First, Semenov term. Let me call it Semenov mass. So this was like ms times sigma z, and under parity, this is going to go to minus ms times sigma z, whereas ms times sigma z under time reversal is going to go to ms times sigma z. It's not going to change. Similarly, the second one, Haldane term. I have mh. I think I use tau z sigma z under parity. Tau z goes to tau z, and sigma z goes to minus sigma z, right? Sorry, so this is parity. This thing is also minus, right? Okay, I messed up here because we said momentum, right? When momentum changes sign, let me put it a little bit more dramatic. So when momentum changes sign, tau z goes to minus tau z, and under parity, right? If you exchange these two things, p goes to minus p, so you are going to have also minus sign here. But whereas here, I think this one is correct. So this one is correct, this one is correct, this one was correct, this one is correct. Okay. Now I can think about this Haldane mass. So this is going to go to m Haldane minus tau z minus sigma z, so which is equal to m Haldane tau z sigma z, which is unchanged. And lastly, m Haldane tau z sigma z under time reversal. It is going to go to m Haldane. Tau z is going to go to minus tau z, and sigma z is going to go to sigma z, which is going to be minus m Haldane tau z sigma z. So the upshot of this, because previously we found Haldane mass gives overall topology, not the Semenoff term, right? That's what we found. From that result and this symmetry argument, we see that broken time reversal is necessary for topology, but not broken parity. So that's the message we got from this long discussion. Now the question is, can we engineer a topological phase without broken time reversal symmetry? Okay, so that's what I want to talk about for the rest. And so in this case, we want to preserve both P and TR. And that's actually a non-trivial question. And this one was answered in 2006 by Kane-Mele. I mean, I don't know for your age, this could be like quite old, but in the history of condensed matter, this is very recent, right? 2000s is like nothing. Even like I think 90s and 80s is recent. So this also shows that like something very simple has been overlooked for a really long time, and these guys actually brought it up. And I don't know if you keep up with these things, so it is likely that this guy is going to get the Nobel Prize in the next 5 to 10 years. I don't know. That's my prediction, but keep an eye. So, and their suggestion was like you have sublattice plus you have valley plus, and they also said let's include spin degree of freedom. Spin is up or down. It's also like a two-dimensional 2 degrees of freedom. And what they said is like in the Haldane mass we have this sigma z. Actually, let me write it the other way. So let me just first write Haldane term. So this is H B Fermi tau z sigma x px plus sigma y py plus, since Semenoff term is not important, I'm going to drop it. There's like m Haldane times tau z sigma z. So this is standing, because I have tau and sigma, this is standing for both k and k degree of freedom. What they said is like, let's say this is for upspin, right? Let's say this is the Hamiltonian for upspin, and I want to double this Hamiltonian with downspin, and I want to put like a minus sign here. So what this is doing is like Haldane term, when you do the time reversal, m goes to minus m, right? And in one Hamiltonian, m goes to minus m, and this is going to negative of itself. But in the other one, m also is negative, so minus minus is going to be plus. So h up is going to go to h down is going to go h up, and overall time reversal symmetry will be protected. So that's the basic idea. And for that they call this, so this term and this term. So let's combine these. I'm going to call them M Kane-Mele mass term. It's going to be tau z for value degree of freedom, sigma z for sublattice degree of freedom. And now I introduce one more Pauli matrix. This is SZ, and SZ is up or down, or plus or minus 1 for spin degree of freedom. Now let's think about this S. So spin is like angular momentum, right? It is like kind of like R cross P. And if you forget how spin behaves under parity and time reversal, you can derive it really quick. So R cross P under parity. So R goes to minus R, right? P goes to minus P under parity. There are like two minuses. Then this is going to go to R cross P. So then spin under parity is invariant, whereas R cross P under time reversal. R goes to R under time reversal, but inside P there is like time. It's going to go to minus. This is going to go minus R cross P. From here, what we are saying is like SZ under parity goes to SZ, and SZ under time reversal is going to go to minus SC. And this extra minus is going to compensate the minus coming from the Haldane term, so that the overall Hamiltonian is going to be invariant. Now we are thinking about these two copies. Let me just take this. Okay. So we are thinking about these two copies of Haldane term. So now I want to think about what about the H states? What is H state like? Because if I can understand the H states, right, the number of H states I can count is going to be the topological number, and that topological number is going to be my sigma xy, which may or may not be quantized. And for that, let's think about like a two-dimensional system like this. So this is for one spin, if you want, this is for up spin. And I am also, okay, and there's like some H state here. Something like that. And suppose I choose mass in such a way that effectively these H states are going to be circling counterclockwise. So this is for up spin. I can also do exactly the same thing for down spin. So this is down spin. But in that case, the electrons, right, mass is inverted. If you want, you can think about like magnetic field, some like effective magnetic field being inverted. And if that happens, the H states are going to also flip. This is like that. And I draw two things, but they are actually laying on the top of each other, right? This and this, they are actually the same sample, and they are exactly the same thing. So that means charge H current. So there is like something like, what did I use here? J charge up is equal to, right? Charge current here is going, for example, to the left here, and charge current here is going to the right. J charge down. And from here, what can we say about J total? 0, right? Then if 0 H currents in total, that means sigma xy is 0, right? There is nothing quantized. Is that all? can we say anything about? Anything else? Any other degree of freedom we can protect by looking at this? Let's also think about spin current, right? Charge is not the only interesting thing. We can also think about spin current. So J spin up is what? It's, let's think about this. Let's call this side minus V. So it's going with minus V, and this is spin up, and spin up is plus h bar over 2. And J spin down, so this is going in the V direction, right? So this is V, but spin is down, so minus h bar over 2. And if you sum J spin total is J spin up plus J spin down. Is it 0 or non-zero? There's like 1 minus here, 1 minus here. If you sum them up, this is non-zero. And if there is like a non-zero H current, that means topologically non-trivial state. Good. Any questions? So a little bit of terminology. So previously, like usual quantum Hall effect, or the usual, also like this is also anomalous quantum Hall effect, the Haldane case. What we had in that case is like chiral H states. So what that means is like there's only one direction for H states, and the other direction is strictly forbidden. But here, in Kane-Mele model at least, we don't have a unidirectional current. We have like both, like flow in, we have flow in both directions. But flow is locked to spin. So if you are up spin, you are going in one direction. If you are down, you are going in the other direction. And the previous case was called chiral. This one is called helical. So this is a little terminology. So this is helical current. And also here we have spin Hall current, or spin H current. And previously we called anomalous quantum Hall effect. This one is called anomalous spin quantum Hall. Okay, a little bit states if you want. Now I want to like think about this H state a little bit more. Like what protects H state from backscattering? Like let's consider backscattering in H. So when we first start with the usual quantum Hall system, in the usual quantum Hall system, we said we have something like this. We have one H state here. So this is like if you draw lambda levels, they come and they disperse towards the edge. And you have another one here. If you draw lambda levels, they come like this and they disperse because of the edge. And if you draw the Fermi level here and there, right? This is like positive velocity, it's going up in velocity. This is negative velocity, it's going down with the velocity. And if you put like an impurity here, this guy cannot go all the way to the other end of the sample and scatter, right? For this guy to scatter, you need an available state in the backscattering channel. But the backscattering channel is on the other end of the sample, so backscattering is strictly forbidden here. So that was the usual story. So this is usual quantum Hall effect. But here, that's not the case. Here, we have like both forward channel and backward channel, right? Because one, we have like 2 degrees of freedom, one is spin up, the other one is spin down, and they are at the same location. And the question is, what prevents backscattering in quantum spin Hall effect? Okay, let me think about it a little bit. So here is my H. Let's think about one H. Okay, it's something like this. And I have one, let's say red is one spin and blue is the other spin. They are overlapping, but I shifted a little bit to demonstrate. And the dispersion is something like this. So in the Landau case, we have only chiral case, right? There is only one direction. But in this case, so if this is K and if this is E, for example, red is going to go in one way, like this, and blue is going to go in the other way, like this. And our question is, how can we just not, right, these states are at the same energy and at the same location, why would they not couple and give something like this? And something like that. Actually, let me just erase this. And the question is, how can I not have something like that, right? If 2 states are in the same energy and in the same location, there will be all kind of crap happening here, and they are going to couple. And when they couple, right, this is like a 2-level system. In a 2-level system, when there's like a coupling, you are going to open a gap. So let me give you a little bit short answer, which is easier to understand, and let me also later be a little bit more technical. Short answer for scattering. So there's like an up spin here, up spin, right? Up spin cannot go and stay up spin like this. So this blue is only for down spin, and red is only for up spin. For scattering, up spin should flip to down spin, right? You have to have this. There's no way you can go to other side. Then the question is, can I just flip spin, right? Is this possible? And remember, the whole thing was brought up from presence, in the presence of time reversal symmetry. So in the presence of time reversal symmetry, right? So this is now elementary question in the Griffiths level. What happens to upspin? Or if I think about any Hamiltonian you have ever seen that takes upspin to downspin, does that Hamiltonian preserve time reversal symmetry? Right? Does it or does it not? This is now elementary question. Even if you don't know anything about this, if you read Griffiths, this should be able to be discussed. So what kind of terms flips spins, right? Like let's think about a Hamiltonian that flips spin, right? There's only one Hamiltonian we spend quite a bit of time, right? There's this h dot sigma for spin, right? There's if you want magnetic fields, and there's a spin, and that's this kind of Hamiltonian. That's the only kind of Hamiltonian that can flip spin. There's other ones, but let's be a little bit simpler here. And does this Hamiltonian preserve time reversal symmetry? And there are two things, either yes or no, right? 50%. You can go wrong 100% of the time.
You say yes, I will say
Okay, then you are right. It breaks time reversal symmetry, right? So if there is time reversal symmetry, this is not possible. And if this is not possible, this backscattering is forbidden by symmetry. Again, the name we call for this is like topology. In this case, quantum spin Hall effect is protected by symmetry. Right? And in this case, symmetry is time reversal symmetry. And last time, for example, in the SSH model, we had topology protected by chiral symmetry, and we call them SPT, symmetry protected topology. And such systems in the broader class are called topological insulators. So this is just one example, and I actually simplified the spin picture. Spin picture is a little bit more complicated. We actually have to, so this up spin, down spin is like spin rotational invariance. Even if I don't have spin rotation invariance, I can repeat these arguments. And there are many phases that can be written down in such manner. And the zoo of phases you can generate is called typically topological insulators. So let me skip. So there is also like technical discussion for this. You can read the book for that. But let me also give you one last important flavor. So there are like two states here, right? Let me just gap is forbidden by symmetry. So what this means is like if you have like a state like this, so you cannot go to a state like this as long as you have time reversal symmetry. But now suppose we have a pair of up spins going in one direction and a pair going in opposite direction for this, right? Rather than like this picture, let me just copy. So I want to take this picture and I want to double each current. So rather than this, suppose I have two up spins and I have two down spins. Right? In the lambda case, this is allowed. Right? In the lambda levels, I have many H states, and number of states that's crossing the Fermi level is going to be quantized Hall conductivity. Then it is like reasonable that I consider something like that. And in that case, what is going to happen is like I have, let me also duplicate this. So in that case, I'm going to have two of these. One is like that, and the other one is something like that. I think, let me do it the other way. And let me shift 0 here. 0 is going to be something like that. Right, two, rather than one, I have two, and if I have two H states, right, these H states need to shift. They, because of Pauli exclusion, they cannot be in the same state, and these red 1 and red 2 needs to be shifted a little bit so that they are a little bit different states. And the question is this also protected, right? Is this also protected by symmetry? This is a little bit more complicated, so I'm not going to ask you. But the idea is, so this one, these are so-called time reversal invariant momenta. Right? These time reversal invariant momenta are protected because when you do time reversal symmetry, one goes to the other one, and that's fine. But these, which are not time reversal invariant momenta, these are shifted momenta, they are not protected. So these are not protected. So if you want, I am actually using this Kramer's theorem that we talked about a while ago, and that theorem is not valid for this. So these states can be gapped out because they are not time reversal partners of each other, and they are going to couple, and when they couple, what is going to happen is something like this. So this thing is going to go. So I need to open this gap and this gap, but this is going to be fine. So, and the picture is something like this. So this one, oops. So this one is like that. This one is like that. There's another one here, and there's another one here. So you can see I protected this, but I opened the gap here, and if the Fermi level is here, so this is E Fermi. Basically, you don't have anything crossing the Fermi level. If there is nothing crossing the Fermi level, you basically gap out these states, and these states are basically killed. And this means edge current can be 1, right? In this case, sigma x y, this is spin, is going to be E square over h times 1, or 0. In that case, this is going to be 0. And this is a binary number, right? Previously we had z, which was 0, 1, 2, dot, 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 as the quantum number. So this is usual quantum Hall effect. But here we have so-called z2. So it can be like 0 or 1. And sometimes these are called z2 topological insulators. Okay, let me give you one last picture of how this is related to topology. And this thing is actually about twisting of the bands. And this twisting should remind you geometrically. So this is like a cylinder versus Möbius strip. So like cylinder or like a rubber band is something like this. And if you want, like there is like something like here. So this thing has how many edges do I have in this cylinder? Like edge is like this, right? There is one edge here, another edge here, like 2 edges. Or I can also count the surfaces, one surface inside, one surface outside. There's 2 surfaces. But this kind of ribbon is not the only thing I can do. What I can also do is like something like that. I can put like a twist here, and I can just connect like that. So this is like coming like that. So this is, and here, so this is Möbius strip, right? So how many edges do I have in the Möbius strip? Exactly. So there's like one edge. So if you have never seen this, you put your finger and just, I think the best thing is just you can roll a piece of paper and like glue it to see this yourself. You just go through this, and then you go to other one, and then if you just keep going, you are going to just come back to yourself. And as you just go, if you come back to yourself, that means there's one edge. And similarly, if you start on this face and keep rolling, at some point you are going to find yourself inside. At some point you are going to find yourself outside. That means there's also one surface. And now you can do one more twist. If you do one more twist, you don't increase edge or surface. If you do one more twist, you are going to go back to yourself. Because two twists, inside going to be outside again. Two twists is basically equivalent to no twists. Okay, two twist is equivalent to no twist. And this is exactly what's happening in the quantum spin Hall case, right? In the quantum spin Hall case, you can put one twist, one chiral edge mode, but if you do one more twist, you do one more chiral mode, they couple and open up a gap, because two twists is equivalent to no twist. And this is also Z2 invariant. Okay, any questions or comments? So this is a little bit beyond undergraduate level, I know, but if you have the appetite, there's like many more things to be learned. This is just tipping your toes in the water. There's many more stuff to be going through. So don't be mad that I showed you too many stuff, but there's like a whole world to learn about it. Thank you for your patience. I appreciate